Okay, so let's get started with the second talk of the session. I think Daniel already set the tone. You saw that we had quite a lively discussion on topics that are actually quite important and relevant to the practice of verification. And Victor will be continuing this same theme. Victor's done a lot of amazing work on decision procedure synthesis, Scala verification. Again, some of the themes he'll take up will echo what Daniel said. So Victor will be talking about stainless as a verifying compiler.
Thank you, Shankar. I will indeed be talking about stainless, which is a verification system for Scala. And it's my pleasure to tell you a little bit about it, since we've been working for it essentially over 10 years. I've been at EPFL since 2007, and so I'm currently actually at a sabbatical at Institute of Science and Technology of Austria, ISTA, and I'm soon going back to EPFL. And I'm going to tell you about some aspects of stainless and why I think it may be a useful approach for writing code that you intend to be verified. So stainless is an open source system. You can get the system, the releases, documentation, tutorials, and so on from this link. And you could classify from the point of view of verification the tasks that it does as verifying safety. Specifically, it works with functions in a programming language, but these are computable functions, so it can prove that certain property holds for all inputs of this function. And it aims to both find proofs of this fact and counterexamples for these facts. So it does both of these things in parallel, because often we don't know which one will be the case. We often hope that there'll be a proof, but we discover that there's a counterexample. And then it also does a program termination. So basically checking that executing these functions eventually terminates. Now, the input to stainless is Scala, which was designed by Martin Oderski at EPFL. And you could argue among languages that emphasize functional programming, it's according to many ranking lists, it's number one. So it's a memory-safe language, and it's strongly and statically typed. And we aim to verify a code that represents not only some abstract algorithm, even though that's a good use of stainless as well, but also a piece of code that you may actually run. And so the way you can run it is either use the Scala compiler and run it on JVM, or there's a Scala native compiler that goes through LLVM. And we also experimented with our own source-to-source or tree-to-source translation that emits C code. And to already relate it a little bit to what Daniel was saying, for us both, the part of mapping of the subset of Scala to some semantics that we want to work with, some trees that we later want to give to lower level or more optimized solving engines. So that's the important part, as well as building these solvers. And part of the system called Stainless builds on a system called Leon that we had in the past, and one of its defining characteristics is to do this separation to some extent. And you will see what our current intermediate language that separates these two phases is. And then we are actually interested in putting horn clauses at that step as well. So I would like to try to give you a concrete flavor of Stainless. And so I'll see if we can have a little demo. So first, just to safely show it on the slide. So this is a definition of a list in Stainless and Scala. So list is an enum or algebraic data type that has the nil case, empty list, and then there's a cons case that has head and tail. So it's a recursive algebraic data type that happens to be polymorphic here over with type parameter t. And then we define a map. Now map is here listed as a method, so it has the receiver parameter. You can imagine that there's something called this of colon list of t. Okay, so that the t list of t is one parameter, and then it takes, of course, a function being a map in the sense of MapReduce and functional map, And this function maps t to u, and the result is list of u. And it's defined the way you would expect, right? Empty list maps to empty list, and if you apply the function to the head, and then you do it recursively. And I'm going to then also define size here, and this size is computing the size of the list and asserting here. This is a form of assertion that states that the result of the function applies the given, satisfies the given predicate. That's stated here is an anonymous function, saying its argument is greater than or equal to 0. So we are saying that size is non-negative. Okay, and we use begins here. We can also use longs, ints, and so on, various other numerical types. Just begins are actually quite nice when you think about sizes of lists. And so let me try to see whether I can actually have this code here. So here I have it in this part of the buffer. I'm going to just run Scala compiler on it just to see that, so that you see that it is a valid Scala input. And then I'm going to run stainless. So Scala compiler said, yes, it is fine, Scala code. Here are some class files that you can run on JVM. And I'm going to run stainless with some default configuration parameters that I put in a config file. And so what stainless does is, since I wrote a code that has some pattern matching, it's going to check completeness of this pattern matching. It's going to check termination by discovering and proving the decreasing measure. And then it's going to check the post condition of this size function, saying that the size always returns a non-negative number. And so this is the typical kind of code that we like to write in stainless when we can, when it's appropriate. It's functional, and it contains some specifications that we can then use for these inductive proofs. I could try to prove that the size is greater than or equal to 1, which of course doesn't hold, and then I will get that this is invalid here, as you can see. And if I move back, I also have a counterexample saying that, well, for the input that is appropriate list, and then I will get this counterexample. So the nil is a counterexample here. And so then I'm going to move and try to show something more interesting. So I have a zip on 2 lists. Okay. So now this zip is written as an external function to this class. So it takes 2 lists and computes the usual zip, I would say. So if I pattern match on both functions at the same time, and then what I do is I put the first elements of the 2 lists in a pair, and then it invokes it recursively. And now zip is actually a stainless library function, so it has a lot of standard list functionality, but it's written from scratch, and it has some specifications inside. Here we have a map function on this list, and what we can do is say that when I take the resulting zip list, which just to distinguish these 2 lists, I have one list of ints on list of booleans. Then when I take projection, this is an anonymous function that does projection, then I should get back the first list. Okay. Now I would like to make sure that you can hear me and that you follow what I was trying to write, because it's just a very basic Scala function, but maybe it's the syntax is a bit unusual. Are there any questions at this point? So yeah. No. I didn't hear. Was that a no?
No questions.
Okay, very good. So then in the meantime, I have in the buffer, I have uncommented zip, and it ran with this extended thing. And so what do I have here? So it says that certain things are invalid. So there are several things that are invalid. One of them is still my post condition here. So let me fix that. And then it says only one more thing is now invalid. And what this is this one. So I could in principle go and see, and says there's something that goes wrong with this post condition here. And I have a counterexample. Again, somebody say or identify what the counterexample is. Why is there a counterexample for this? I zip 2 lists and then I project it, I get the first one. So when does it not hold? Okay, so a counterexample is just a list of where the first one is a list of length 1 and the second one is list of length 0. And so then the zip will stop as soon as it turns out one of these lists. Yeah? And so that's what the tool found. So I'm going to say, well, zip shouldn't really be called on these kinds of lists because I really want to use it so that it satisfies this property. And let me say that actually I only want to ensure that the size of first list is less than the size of a second list. So I'm going to put that, and now it verified, and you see there are 0 invalid things, and so it proved this property. Okay, and so that was the simple session to introduce the tool. What I think is maybe interesting about that is that this code was written and compiles with a standard Scala compiler and an interpreter. So the specifications are valid Scala, and they just become dynamic assertions when you compile code. And we had multiple recursive functions in code and specification. So actually, this example, I said that there's a library. Of course, you could have lists in the library, but this particular example was fully self-contained. Yeah? So zip, size, and map were all there. You have seen them. And so there are multiple recursive functions, and Stainless is able to take into account all of their semantics in order to prove the property. Map was a higher order function. And you saw that when we couldn't prove the property, then there was luckily a small counterexample, and the tool was able to find it. And it was along the way proving all functions terminating. And now I didn't try to break that, but maybe if I just go to map and say do something silly, like I call myself on the same argument, then I basically failed to find a valid measure on the map function, and then it complained. Okay, so it also shows a termination of all the aims to show termination of all the functions that it's working with. And what I didn't show that in this particular case, actually, it's nice to look at what output it gave me. It actually found also a counterexample for the or at least in some cases it finds counterexamples for non-terminating functions. Yeah, here. So it was here. It actually sometimes checks that for certain values it gets an actual loop, and that's of course not something as a given that we should be able to find these, but in some cases it manages to do it. So this is in a nutshell the functionality of Stainless. So what have we been using it for? You can see an overview of some more interesting examples that are public on this website. And they include various balance trees like red-black trees, and showing that they are isomorphic to lists of key value pairs, for example. And more complex instance of that are conc trees, which are trees that support very efficient concatenation while being functional. And they were described in this not so old paper in the Conference on Parallel Computing. And they served for a while as a basis of the library for parallel collections in Scala. We've also shown correctness of some mutable hash tables. And so usually we aim here for the stronger specifications, because Scala is a memory-safe language, so there's not that much to show there. We could settle for showing absence of various runtime errors like array bounds and so on that would crash your program with dynamic error. But often we sort of get more excited and try to prove more complex properties. So one such example is a quite okay image format that you may have heard of. It got quite a bit of traction through Hacker News and other forums, because it's a very simple format for lossless compression of images that was implemented in only a couple of hundred lines of C, and then re-implemented in dozens of languages shortly afterwards, sort of as a reaction to complexity of some other image formats like PNG and so on, because it was shown to be very fast, faster than those, even with a simple short implementation, and also also work so well in practice in terms of compression. And so what we did is we wrote in Stainless this version of this algorithm that is compatible in that it reads and writes these compressed files that you can you generate using any other implementation. And then we proved that that if you encode an image and then decode it, you get back the same image, which is something that, because these are functions, right, implies that you are not losing information here. And that's one of the, I would say that's really most of what you would like in terms of functional correctness of code like that. And this is a very interesting area. We are seeing actually formal methods being used more and more because this is clearly important. Application domain, this is just one example. And having domain-specific languages and further automation approaches for this, I think is really going to, is really taking off. Some other examples that we use Stainless for are more soundness proofs of type systems. So this is really a proof that is not so much about computation, even though most of it is expressed in terms of computation. Inductive proofs become recursive functions in Stainless. And so in this case, it's soundness of system F. And so this happened to be a class project among the more successful class projects. And I was happy to see that this worked out. And then through some master thesis and collaborations, we have had verified versions of certain clients for blockchains. We had a version of actor library that was specified to set in terms of high-level properties, and then you can write applications in terms of those actors. And another example was this case study that we did with a company called Atelaris, and that was supervised by European Space Agency, where we rewrote part of the file system for flash storage on board STIX solar orbiter, which is an instrument for X-ray imaging. And so the C code was already written. So what we showed that you can rewrite parts of this in terms of Stainless and regenerate C code, and that this serves as a valid replacement in terms of performance and functionality. So we detected a couple of small bugs in the process, but the main thing was that it actually worked as a methodology. And so as I mentioned, we've been working on it for a while, and I just wanted to give here thanks to all the past PhD students of Lara, most of which had something to do with Stainless and its predecessor, Leon, as well as my postdoc Jad Hamza, who did some very important work, as well as Mario and Roma, who were engineers, and Mario is still working in the group. And so I wanted to the extent that time permits, say a few words about what happens inside. And maybe it's good that I have at the beginning that one of the design aspects of Stainless, which is that it works by doing precise compilation to logic, something that I think is similar in the spirit to Daniel saying not doing too complicated things. I would say maybe what we are doing now is indeed more complicated, but I don't see a much simpler way of doing it at the moment, hopefully in the future. But at least we preserve some key properties. In particular, we are preserving the determinism and the functional input-output behavior in some sense while we do this compilation to logic, and only then we do solving. And so if you were to draw some sort of a diagram how the Stainless works, it takes these Scala programs with some contracts, and then it looks very much like a compiler with various phases, with a pipeline of phases, and they remove high-level constructs that also a compiler that aims to execute code would need to remove, because, well, simply that's the meaning of these constructs, whether you execute them or you prove them correct. And then, among other things, we also encode imperative reasoning in terms of functional reasoning. And I'll say a little bit more about that. And so there's a number of things that happens in this form. That's maybe most of the complexity in terms of lines of code. And then at some point we get to mutually recursive functions that can still be higher order. And we call these trees Inox trees because they're given to the solver called Inox. Now, there are two parts that that are going on here. One is that there is a description of all these recursive functions, and then there are assertions still inside these functions, things like post conditions and explicit assertions. And so that's why we have this verification condition generator that then encodes a property that together is sort of like a top level program, if you wish, that together with these recursive functions constitutes a query to Inox, which then proves it correct. And you can think of Inox to a large extent as a kind of alternative to horn clause solver or something like constraint horn clause solver, but restricted to functions and permitting higher order functions. So it's similar to some of the intermediate verification languages, but not based on guarded commands. And now these verification conditions are there to ensure that we check in a sound way all the properties without circular dependencies and taking into account the termination constraints. So maybe I could contrast what we are doing here a little bit with Daphne, which is a great system and that is maybe similar in a lot of ways to what Stainless is doing. So my understanding that Daphne still goes through the bulky intermediate programming language that is based on guarded commands, and it uses background axioms. And then this ultimately, when you then verify the generated intermediate code, you obtain quantified SMT queries. And this approach actually, if you tweak it correctly, seems to work really well for doing proofs. But it seems to be harder to obtain counterexamples using this approach, because here usually there's some over-approximation that happens. And also here, when you obtain quantified queries, it is a priori not to be expected that SMT solvers can find counterexamples in this case. Now, this is partly a sort of theoretical consideration. In practice, you can get counterexamples from these other tools, but I think that seeing that you can also do this translation in terms of functions is interesting as an alternative design point, and that's what we are following. So in our approach, we translate program and its specifications, which in most cases are executable, into a functional, purely functional program. And then we use a solver that we call Inox for these functional programs. And what Inox does is encoding into SMT lib queries and invocation of SMT solvers. And for now, it's only invoking SMT solvers on quantifier-free formulas, which means that we should expect that we get counterexamples. Things can still get slow, but in principle, these queries that we generate should be in decidable fragments. Well, when we don't use multiplication of unbounded integers, for example. So here the idea is that if you think about soundness, so we haven't proven the soundness of these transformations, but if the soundness would be something similar to soundness of a transformation path in maybe composite. So that you preserve just the behavior, you don't need to think so much about verification when you do that, but you're mostly concerned about program behavior. And now then what Inox does, this unfolding of recursive functions, you can think of it as subsuming forms of bounded model checking and k-induction. In terms of termination, I will maybe get to say a few words about that, but we basically guess certain measure functions, and then we prove that they decrease. And we have some techniques to do that even interprocedurally. Maybe just to go over one example of encoding mutable state. I will show you the encoding that is more recent. So by default, we use a linear model of state that is maybe more similar to Rust than C, where we disallow sharing. But we have, as of recently, the model that allows sharing. And in that case, we would introduce some notion of heap type that is essentially backed by an array. So it's again related to what Daniel was saying. And if you have, for example, some procedure that adds here to values from the mutable cells, then this procedure would get an extra heap parameter, and it would return an extra heap parameter if it updates this cell. So here we have a cell update. This becomes update to the heap in the expected way, and we are returning the new heap. So this is not really surprising. If you did it everywhere, you get a sort of a state monad. And so one thing that I would like to highlight here is that when you think about what is known in terms of decision procedures, what is implemented, then you can sometimes go further in preserving these counterexamples. So to reason practically about these heap modifying functions, one approach is to use reads and modifies clauses, like in Daphne and many other tools, and that's the one that we adopt here. But if you look at one way, a typical way, I would say, of encoding the meaning of these modifies clauses, it would be that here I'm encoding the reads clause. Okay, so reads clause says that basically you're only reading cells C1 and C2 and nothing else. And so one way to say it is that if I then were to invoke function on some other heap instead of this heap H, and if these two heaps are same on these two cells, say C1 and C2, then what I would get as the actual int result here, that's why it's projection, because in the encoding it's a pair of the integer and the new heap. So what I would get as the integer result would be the same, because the two heaps H and H prime are the same on what the function reads. Now there are two quantifiers here. One is up over the heaps. Now that's something that we can maybe choose to instantiate ourselves by saying that we have specific heaps of interest. And the other quantifier is over all possible references in the heap. And that's the one that we would like to get rid of further, so that we have no quantifiers. And the idea that we use here is to adopt a combinatory array logic, which is a very nice and very expressive logic of arrays implemented in C3. So here's this the original paper that describes it. And you can think of it as a decidability result following from a form of theorem in model theory on products of structures. But what it does is it extends the usual theory of arrays, which is stated here. We just store, if you store some value, you get it back. And if you read back something else, you get what was there before. With some additional constructs, in particular, the map combinator, which really is more like an n-ary zip on arrays, that says that I can combine these two arrays using some function f and get something that is defined pointwise on all the elements. And so among wonderful things that you can do in this logic is implement sets and multisets. So let's say if I want to implement union, I would say, well, that's just pointwise disjunction. If I represent my set as array from into Boolean. Okay, so just from characteristic functions for sets and this combinatory array logic, I get these set operations. But what we want to use it is something called map merge. So what we found is that we can define map merge operation using generalized arrays, which takes a set, you think of it as some mask, and two maps that represent, for example, program state, and then compute a merged map where the mask basically says how to merge these two things together. So you have a zip that's conditioned on this set. And so that means when I have 1 in the set, when something belongs to the set, I take A. When I have 0, I take something from the other one, the Y, and so on. Okay. So that's something that's expressible because it's really defined pointwise. How? Well, turns out there's if-then-else operator. That is a ternary operator that takes a Boolean and two values, and well, it implements if-then-else. And if you map if-then-else operator over this set and over these two maps, then you get the merged map. And this merged map, when you think about it, that's a sort of thing that we are used to in program analysis when dealing with state, right? So interprocedural program analysis in particular, that's also what we get for frame conditions. And once you have that, then you can quite naturally express reads and modifies clauses. And so so that's essentially what we have, and that's one way that we preserve this determinism down in translation to simpler purely functional programs, even for things such as reads and modifies clauses that traditionally, I would say, have been expressed using, at least in this first order logic-based formalism, expressed using quantifiers. And let me now get to this Inox part, which is solving certain verification conditions involving recursive functions. And so this slide explains what it does and how it does. It searches for how it does both form of key induction and search for counterexamples. So suppose that I have a function f of x that's defined. So I have def of x in my programming language. It's defined as some function body that contains a recursive call, let's say on x minus 1. Okay? And I want to prove that it's x greater than or equal to 0. That the result, it's not really x, but the result is greater than or equal to 0. But I'm going to focus on what we do with this definition. So of course, being a recursive definition, I can unfold this f again, and then I would get in place of f again e of x minus 1, f of x minus 2, and so on. This process could go as far as I need it for my argument x. And then Inox does this iteratively, starting from no unfolding and then unfolding gradually. The fact that we can soundly conclude something about no unfolding is actually because we are working with this functional intermediate representation. And so the check for counterexamples replaces this innermost recursive call that we don't want to unfold yet with, I'm using here notation bottom. This is just a notation for generating a version of this expression that in first order logic blocks all the branches where I would do a recursive call. And so that's what we implement using some extra Boolean flags in the SMT formula. And as a result, if I know that this formula is satisfiable, if I want to check, for example, whether it's possible to get that something is equal to 42, then I know that this is indeed a real counterexample because I didn't go through any of these functions that I didn't unfold yet. So I got a finite execution traits as I would in bounded model checking. It's just that this process is based on unfolding recursive functions, so you end up getting a different unfolding than if you transformed everything into a control flow graph. And the other check that we do is an over-approximating check, where this innermost function call is just replaced with a fresh constant. And then in addition to that, the calls in between, when we have some post-condition specification, they're assumed to be satisfied. So we assume that all the recursive calls before they satisfied the specification that we are trying to prove, and then we try to check whether our conjecture is true. And so that's an over-approximating check. And by switching the values of these Boolean variables that we use in encoding this and this, so this is actually one shape structure, it's one formula, but by just setting Boolean variables differently, we get one or the other, and we can ask for expect a set or unset check to give us the desired answer. And then there are other aspects of this procedure of what's happening here. This is just encoding of recursion. We also have encoding of higher order functions, among other things that are encoded using a version of dynamic dispatch that preserves all executions. So that's here, and maybe to relate it to constraint horn clauses, you can see that a large part of what Inox is dealing with here is recursion, and horn clauses are also ultimately recursive constraints. That's how the existence of inductive invariance is expressed. And so I think it would be interesting to consider adapting this part after the encoding into horn clauses. And I think that given that we have competitions of horn clauses, we can work to avoid the fact that that we have different benchmarks aimed for very different solvers. I think we will need many different techniques and many different solvers, but at least we can compare them. And for this high level reasoning about functional programs, we don't want to have just bit vectors and arrays and uninterpreted functions. We want to have also things like algebraic data types, which we use directly as theories of algebraic data types in Z3 and CVC4. And we want to use other available data types. So, because that's where the people have put in effort to actually derive consequences of the axioms that define these theories. And that is something that can really speed up our verification effort and success rate. And so I don't know how much time I have still. Check it roughly. Okay, so I'm actually not hearing anything, but if hopefully I'm coming through. And
so Victor, can you hear me?
Yes, I can hear you now.
Yeah, you have about 10 more minutes.
10 more minutes, okay. So I'm going to just quickly say a few things about the foundations of the system. We were inspired to look more closely at foundation when we realized that termination in the presence of higher order functions and the kinds of definitions, data definitions that you allow in object-oriented programs, that this is a very interesting problem and that we need to address it properly to have a sound system. And so, why do we need termination to start with? Well, for a lot of cases, actually, you would get a meaning. You could interpret meaningfully the answer of a tool without checking termination in terms of partial correctness. But when we do more difficult proofs, we end up convincing statements that something is true using inductive reasoning. And then this code is there just to convince stainless. It doesn't actually execute. So we would like to have it there as a call to make verification conditions be true, but we want to erase it. And this erasure would change the behavior of the code if it was not terminating. So we would turn something that was, in case, of course, this specification code is not terminating. So as you would expect, maybe from experience with proof assistants, these specifications should normally terminate. And also a lot of code naturally it has termination as its requirement, if not even execution time bound. And so we want to have termination, and we would like to do it to check it one function at a time. Now, this is one design aspect of stainless, that it actually will check every function based only on its preconditions currently. It's not going to try to infer the context. And so in that sense, it's a simple modular checking. We would like to have similar thing for termination, so to check things starting from a given arbitrary values of the function to satisfy precondition. And we'd of course like termination for all possible arguments. Now this is a generally difficult problem to do, to solve. So if I have also might be even difficult to define what the problem is, right? So what is the expected behavior? If I have a higher order function like map, so should this map be considered terminating? Well, this is a correct implementation of map, and I would like to consider it terminating because it's nicely traversing the list. Of course, if you pass it a non-terminating function, then it's not going to terminate on an empty list. So it's terminating when it's given a terminating function. So you would like to formalize this kind of requirement. And I found the most natural way to do it is using type systems, because there were nicely type systems that were shown to be terminating and that so strongly normalizing. And that's what we use as a starting point. So for example, system F, Girard's polymorphic lambda calculus, satisfies strong normalization. And so that was our starting point. And we then wanted to also support lazy data structures expressed in terms of closures, because that's how they're really used and thought of, I would say, in Scala. So not some sort of co-inductive types or something like that. And so, but then if you try to do strong normalization there, you find that actually many of these functions are not strongly normalizing if you start to reduce underneath lambdas. So that's a bit too strong. And we also wanted to encode directly refinement types and support this function unfolding, and as well as termination checking in terms of measure functions. And so those are the sort of requirements that we had, and we came up with a type system that was presented in UPSL 2019 and formally proven correct in Conc. And that sort of closest to the foundations that we have. You could bridge the gap between the implementation and the foundation further, but that's sort of current our guiding system. To see maybe some of the why things are interesting here is if you have contravariant recursion like here, which is like domain theoretic equation for lambda calculus, you have a class that takes a function that maps D to D. So that Scala compiler has no problem with that. It's a perfectly compilable, executable to have things like that. But if you then write this expression that on its own doesn't have any recursion, then this doesn't terminate. So this is just the usual omega term in lambda calculus. And so how does our type system, for example, work around that? Is well, it's not going to permit these declarations without some extra specifications, and these extra specifications are index arguments. So you could view this as a very limited form of step indexing that you embraced as a sort of throughout the framework in Iris, but here we use it only for certain contravariant recursive definitions to allow them in the system. And yeah, so as I mentioned, the way we have somewhat heuristic approach to check these termination measures, and then the type system can aims to check locally the validity of these measures using sound type checking rules. Okay, and so I would, if I have time, I would just like to point out two directions that are still ongoing work, and we have some results. But I think I expect we will continue to work on them. And one is further automation for certain properties that are common. In particular, if you need to prove a complex property, given that we tend to avoid using quantifiers, often you end up specifying some recursive functions and then doing inductive proofs. And inductive proofs in stainless, they are possible because of this unfolding algorithm, because this unfolding algorithm will, when you unfold function, also assume the postcondition. And if you want to, for example, prove this theorem that says that if you concatenate two lists and look up ith element, then what do you get? You have first list, you have the second list, and here's some index element I. Also, you may get element of the first list, or you may get element from the second list, depending where this I is relative to the size of the first list. And so this is the proof that goes through in stainless. So it's not fully automatic, but it's relatively short, and it's essentially a custom induction on that traverses the first argument L1. So here we have, incidentally, an explicit decreases annotation. So when we cannot guess the termination measures, a user can specify them. And but for example, here this recursive case also doesn't check that I is greater than 0. So really having this unfolding mechanism K induction as a way of expressing inductive proofs is quite expressive, and I would say rather intuitive. And but in some cases you would like to avoid having to write these inductive proofs. They often end up being what makes the proofs long. So we're looking to eliminate them. So one idea is that we can maybe automate these proofs when we are checking function equivalence. And function equivalence is, again, a great property to be systematically proving because specification is so simple. You have two versions of the function. Maybe you have a revised one function, or maybe that one is a naive implementation and the other one more efficient one. In this case, we have actually two solutions of a programming assignment from a data set I'll say a word about. And then as you can see, one uses auxiliary function, one does not. So they look syntactically different, but actually you can prove them equivalent by using one function in the postcondition of another. And this is something that we are looking to automate. And you can automate that on a set of programming assignments. This is the result from the data set. We have similar assignments from EPFL courses where we are teaching functional programming in Scala. And so that's one reason we translated existing OCaml data set to Scala. And you can see here, for example, that we know that equivalence is transitive relation, We're able to use this simple induction approach to prove a whole bunch of things equivalent to one, and then these two were proven equivalent, and these other ones were proven equivalent to this. Even though proving some of these edges did not work out. So it's sort of to be expected that this semantically is transitive relation, but syntactically, because it goes through inductive proof, this direct proof may not always work, and that's why it's interesting to have a system that has higher level understanding of what it's trying to do. And another point that I wanted to mention, since there was also talk about the big proof event that was taking place earlier. So when doing these proofs, in some cases, I would say this induction with auxiliary functions works fine. But in some cases, one would really like to have a more explicit notation with quantifiers. And for that purpose, to have a system that we understand that we can still have high degree of confidence in, we started building a proof system based on set theory. And now set theory is usually formalized using first order logic. And it turns out that the core of our proof assistant was actually to introduce first order logic with schematic variables. And that then proof checker actually knows nothing about set theory. But the axioms that we intend to use are set theory. And the nice thing, so this is still very early in the process, but we are starting to prove some basic properties to bootstrap the framework. One thing that I expect we will be able to do is to express also typed foundations like dependent types using set theoretic embedding, so embedding into set theory. Of course, this will include assuming proof erasure. But there are other successful approaches that have used set theory, including TLA+, right? And so one thing that came up in this proof checker, as well as in stainless when we write auxiliary assertion, is the question of checking equivalence of simple proof steps. Now, let me just give you an example. Suppose that you have a theorem of this form. Okay, so it's negation of some conjunction and disjunction with D. And then I have somewhere in the proof the following statement G. Okay, so now if you look for a little bit, you will see that in fact this call G is a trivial variation of this proven theorem T. Okay. This is T. Why? You just need to apply De Morgan laws and use associativity and commutativity for the logical operations. And yet syntactically, these two formulas are distinct. And so one thing that we did in our proof checker is we said there's an equivalence relation that makes these formulas be the same. Actually, you can traverse them. They are still syntax trees, but when you apply a proof rule, then the assumptions are checked modulo that is equivalence. And now you may wonder, what kind of equivalence did we use? If this is propositional logic, maybe we can just invoke a set solver. They're pretty fast. So we actually wanted to make sure that nothing slows us down, even if we have huge formulas. So we looked at the question of polynomially checkable equivalences between formulas. So we didn't try to show that co and p is equal to p, but we identified a sufficient condition for equivalence. Because if you think about it, if you just reorder or sort order of conjuncts, you will get something that is sufficient and that you can hope to be more efficient than propositional equivalence checking. And the struct we gave an algebraic characterization of the algorithm that we have. It actually precisely checks equality between terms that have disjunction, conjunction, and negation, and satisfy all these laws. Okay. The only law of Boolean algebras that it doesn't satisfy is distributivity. And so all the other ones are taken into account. So if your formula is equivalent by using any finite sequence of these properties, L1 to L8 or L1 prime to L8 prime, then the system will check that. And we call this structure that satisfies these properties orthocomplemented by semi-lattice. And we're also looking at some intermediate things that are stronger than that. But the nice thing about this one is that it has actually really ON log n square algorithm for checking equivalence. And this is the result that my PhD student Simon Guyot showed. And so that's what we have deployed in this proof checker under development. And also we are looking to incorporate it into stainless to have a better formula caching, better assertion checking, and so on. And so I'm interested in many other directions. Now, I didn't say more about horn clauses, but basically they would be, the hope here is that we get more of the reasoning from that we currently do at maybe some other levels at this level that is language independent. And yeah, so that's basically it. Happy to take any questions.
Thanks for the very nice talk. Big round of applause. Yeah.
Thank you. So I'm monitoring also my chat from audio. I'm hearing Shankar very well.
Hello, can you hear me?
Oh, yes, I do.
Hi, so earlier you were talking about having to introduce these heap variables to hand to the solver for like functions that do mutable things.
Yes.
But how much of the Scala that you see in practice is actually just purely functional, and how much really needs this?
Right now, stainless is mostly applied to code that is written for stainless. Okay, so part of the reason is that most Scala code out there will use Scala libraries. And Scala libraries are using certainly mutation internally. We could hope that this mutation is not observable, but that might depend sometimes on how you use the interfaces. So I think the community of users of Scala, in my impression, is fairly pragmatic. So they're using functional paradigm as a guiding principle rather than as a sort of strict requirement. So now this an interesting development is that Martin Nodersky's group is actively working on an effect system for Scala. And I think that's going to now, for the first time, once this is in place, really make it visible which parts of Scala code are functional, which ones are not, even in the broader Scala ecosystem. We check this, of course, we are sound in that respect, but we'll reject many uses of annotated shared mutable data structure access and so on. So, I mean, if you look at, for example, implementation of array of sequences, implementation of trees, the patterns like string buffers, they're included inside there. So there's certainly internal mutation. And I think Scala programmers would not think twice in optimizing some piece of code using some local mutation. And actually, for completely local mutation that does not go through Heap works fairly well in our system as well. So I think I don't have a good numerical estimate of that at the moment, but it's partly language design can influence what people do, and I'm hoping effect system will encourage people to use more functional code in their Scala application.
I have two questions. So that was really interesting. Thank you. Really early on, you mentioned the student project to show soundness of system F.
Yeah, progress and preservation. Okay, I'll tell you what I know. System is online on this GitHub repository, and so it was progress and preservation, but no strong normalization, because that would be a bit difficult to express inside of a system our system, and it uses the brand indices for type and type variables and the terms, and yeah, I think that's mostly. They also prove some other things, but I think that's the main part of it.
So you
but
encoded reduction rules.
Yes. So yes. So there was explicit encoding of type checking rules. So there's a notion of a proof tree that I believe that made the proof simpler.
Did it give you an interpreter for system F?
I believe there is an inefficient interpreter for system F, yes, inside.
Right.
One that goes recursively and would stack overflow. Most non-trivial things.
Okay, I'll touch on that in my talk. There is an interpreter there.
You mean by virtue of the fact that we proved this property, you could tell us, you guarantee us there is an interpreter.
Exactly.
That's very nice. So this, in our case, interpreter is explicit, but I remember we had some proof in COC of soundness of system FR itself, where we felt we had to write an interpreter ourselves, but maybe that was because of efficiency component.
Right, that's an interesting question, but I'll touch on that on Friday.
Great. Sorry, I'm not hearing anymore.
Yeah, that's okay. Thank you.
So, Victor, I have one question about the equivalence checking on student projects.
Yes.
So, what are the results on that? And do you kind of rule out interesting creative solutions because they don't check?
Yeah, so this is not really deployed yet, so it's more like an offline evaluation of what we have had. Most of the limitations, so I think these are fairly small programs. I think we found very few cases where this didn't really, where this would be limiting creativity. Mostly, I would say, because they're relatively simple assignments. And when we had limitations, we attributed it to termination, lack of success of termination checking phase. So it could be that our termination checker is not good enough. And then we could just say we don't care about termination. But I feel that's not quite right. That would be cheating with respect to the objectives of this. Because if student writes a non-terminating solution, and then you could show non-terminating solution to be equivalent to anything if it's sufficiently non-terminating, so to say. But I think that you could deploy this in combination with testing, with symbolic execution. That's what people have done in the past, and that's something you can still do. And then you identify some cases where it's clearly wrong. You identify cases where you have proven it correct, and you identify some cases where the situation is very interesting, so you can focus on those cases.
Thanks a lot, Victor. Thanks again.
Thank you.
Okay, now we're going to take a break for lunch out here. So for those of you in the virtual world may have other meals you want to take care of, and we'll come back